I was simulating the pressure increasing below sea level. That was really dumb. Welcome back. We get another chapter here going on with environmental physiology. This was Hyperbaria. So looking at increases in pressure going below sea level. So below the surface of the water mostly. Now we can go below the surface of sea level without going below the surface of the water. We can go below, I didn't say that right. You can go below the surface, you can go below sea level without going below the water. There are a couple places on Earth that you can do that. Death Valley is one of them. But increasing the pressure, specifically when we go below the water, that's going to cause some problems, some physiological issues that's happening. So we get to see the science behind it, some of the physics behind it, the increase in pressure as we go down. It doesn't take all that much depth to equal the amount of pressure that we have at sea level. So what problems can occur as we continue to dive deeper and deeper? So we go into some of those concepts, some of the problems that can occur, major problems, and then also rising back up to the surface. What problems can happen? Ascending too rapidly, potentially, might have some issues there as well. And there's also a video that I mentioned in there, and it'll be linked down below. It's a 60-minute video of a guy who was deep sea diving, and you can kind of see some of the processes he went through to train for that. And it's kind of a really interesting video. So without any further ado, I give you Diving in Hyperbaria Physiology. Diving in hyperbaric hypoxia. So before we get into the physics of the dive and going underneath the water, a nice little meme or picture that I like to show. I'm a South Park fan. Some of you may know that, but there was an episode where you had this skier that kept saying, you're going to have a good time or you're going to have a bad time. Okay. And it was about skiing and either French fry or pizza or however you ski. Now, the reason I put this up here is because humans plus air and maybe having an increase in elevation with the air, you're usually going to have a good time. There might be some problems that can occur in the altitude chapters in lectures. We go into that. But humans in water, the deeper we go in water, we're going to have a bad time. Okay. Not going to be a good time. And it's going to keep multiplying the further and further we go down in the water. We can't swim down to the Titanic right now. It's just not going to happen. There's way too much pressure, and that pressure builds up very, very quickly, as we'll see. So let's look at sea level. Here we are right here at sea level. So we're at 760 millimeters of mercury. That's what the pressure is at sea level. This is also referred to as 1 atmosphere, or ATA, ATM, either capitalized or lowercase. As we dive down, we have that 1 atmosphere plus the progressive increase in the pressure as we continue to go down below sea level. Now going down 10 meters or 10 MSW, meters of seawater, so going down below the surface of the water, equals 1 additional atmosphere. So as we go down to 20 meters, we're at 3 atmospheres. 30 meters, we're at 4. 40 meters, we're at 5. 90 meters, we are now at 10 atmospheric pressures. So the pressure starts to increase very quickly as we move down. Again, this is only in 10 meters. This entire atmospheric pressure at sea level is from the surface of the water up until you reach space. So you have this huge distance that is causing this one pressure here at sea level. But each time we get down 10 meters underwater, we're increasing it by 1 additional atmosphere. That's astounding. That's how much pressure is being increased each time we go down 10 meters. So we tend to have some physiological problems associated with this, obviously. There's going to be compression of air pockets in the tissues, and even the skin itself could become compressed. And we'll see how that affects the lungs here in a little bit. And keep in mind, we need to breathe oxygen. And it can be somewhat difficult to breathe when our lungs can't expand because there's so much pressure. All right, so let's step this back and look at some of the laws and the properties that we're dealing with here. First off, Boyle's Law, or from Robert Boyle. Boyle's Law states that pressure is inversely proportional to volume, meaning that there's an indirect relationship between the two. So as one of them goes up, the other one is proportionally decreased. So as we increase the pressure, there is a subsequent decrease in the volume, which is what happens when we go down below the surface of the water. If we were increasing altitude and lessening the amount of atmospheric pressure on us, then the volume would increase. So this is seen with a balloon. So if you fill a balloon up at sea level and you take that same balloon up to a higher altitude, maybe 10,000 feet, that balloon has now expanded. There's now less pressure being exerted on that balloon. Now, if you take that same balloon and go below sea level and increase the atmospheric pressure on it, that balloon now gets smaller. So there's less volume there. Now, one way to try to counteract some of this and also to be able to breathe underwater, we have what's known as scuba gear. And just as a note, scuba is actually an acronym. So it's known as a self-contained underwater breathing apparatus, or scuba. The other law that we have is the gas that is dissolved is inversely proportional to the pressure. So more pressure, more gas dissolved. Now let's look at some problems that humans can experience with going below the surface of the water and increasing the pressure exerted on our bodies. So when we look at breath hold diving, and I'll get into and touch on a video, and it'll be at the end of this PowerPoint, but it'll also be down below, and go ahead and click the link on it. It is a 60-minute video describing a deep sea diver and looking at some of the ways that he trains for that. But breath hold diving, so not using any scuba gear, there could be an air embolism. This is caused by a decrease in pressure while somebody is ascending. You are relieving the pressure exerted on the body, but now the volume is getting larger, thus going back to Boyle's law. The lungs will expand, and if the person is not breathing properly, the lungs could expand to the point where they start to rupture, and this is known as a pneumothorax. So there's air bubbles that circulate then to the cerebral cavities, or basically the brain, and is going to cause issues and could potentially cause death depending upon how severe it is. There's also a lung squeeze, so the increase in compression of the lung tissue. So there's this imbalance between the blood and the capillaries surrounding the lungs and the lungs themselves. So the fluid moves to the lungs and the oxygen diffusion is decreased. That oxygen diffusion is very important so that we can get the oxygen into the blood from the lungs, and that decreases. So we're going to have problems breathing and getting the oxygen into the body, to the tissues, but also at the same time, carbon dioxide is going to start to increase, and the tissues themselves could start to rupture. The alveoli, or the little sacs in the lungs where the oxygen and carbon dioxide transfer occurs. There's also something known as face mask squeeze, and this is related to an actual wearing of a face mask going underneath the water. So there's a failure to equalize the pressure during the descent, and the pressure is increasing. So there could potentially be a ruptured eye blood vessel, or the eye itself could be dislocated. Now this depends upon the different scenario, and it depends upon how much pressure was being exerted from how far they went down below the surface of the water. You could also have what's known as aorotitis, or middle ear squeeze. So this is the pressure difference in the oral cavity and the tympanic membrane within the ear, which could cause the middle ear to rupture. So the recommendation here is to inflate the middle ear for prevention of this. So closing the glottis and contracting the pharynx muscles, sometimes known as the Frenzel maneuver, similar to what's known as the Valsalva maneuver, basically exerting yourself without breathing. So trying to breathe out without breathing increases the pressure, and it will help to inflate the middle ear. And this is sometimes referred to as alternobaric vertigo, or disorientation from this aorotitis. Now, looking at decompression sickness, this has to deal with nitrogen bubbles that are going to start to form. So descending causes increased pressure of gases in the lungs, which is somewhat obvious from what we've already seen. And what's occurring is we have nitrogen that's diffusing across the membrane within the lungs that's causing some problems. So it's known as nitrogen narcosis. There's a physical and mental state. It's actually similar to alcohol use and becoming inebriated or drunk. And there's a little bit of euphoria, overconfidence, and poor judgment due to this nitrogen narcosis. So referring this to the bends, so you're ascending to the surface rapidly. It's a very swift decompression. This releases nitrogen bubbles within the cells. Those bubbles are commonly present in some divers. And then this nitrogen is then filtered by the lungs and exhaled. When the nitrogen bubbles become in excess, there's a disruption in some organ functions. And this is sometimes referred to as compartment syndrome. It's blocking blood vessels and rupturing cell membranes within some of those organ tissues. Now, the way to alleviate this is to have gradual decompression, gradually release that pressure on the individual. So the nitrogen diffuses from tissues to the blood and then exhaled, which was referred to a couple of slides ago, in that we need to exhale that nitrogen. So proper scheduling of the different stages of decompression is very important for this. Most often there's an in-water decompression where there's certain chambers that are located at certain points in the depth that help to gradually decompress the individual. Now also keep in mind that the majority of activity underwater is submaximal. So any type of breath holding, there's going to be some risks that are involved, and there's some respiratory limitations. Even though it's still submaximal, there's still going to be some limitations and risks that are involved with it, just not the pressure differences. There is a training involved with this, and a maximal effort is rarely required for any type of physical activity underneath the water or at higher pressures. But most of the time, performance limitations, there's a physiological component to it, but a lot of times it's psychological, in that the pressure is increasing and there could be some potential for being able to overcome those limitations in breathing while underneath the water. That's really the major psychological hurdle to overcome. So the link to the video that is shown here is also down below. Go ahead and click that link. Again, it is from a 60-minute episode from a few years ago, looking at a diver, a free diver, and some of the training that he was going through for that. And that wraps up diving in hyperbaric physiology. And you'll see me in 2 seconds, 1 second, 5 seconds, who knows? 3, 2, 4, 2, 1. And, when I go over this chapter, the one thing that comes to mind, I make movie references all the time, and you know that. One movie reference that always comes up during this is Total Recall. And anytime somebody got outside when they were on Mars, anytime somebody got outside of the kind of containers or rooms or wherever it was on Mars, they had their eyes bug out of their head and everything. I don't know why this chapter makes me think of that, for increase in pressure. I don't know, which doesn't make any sense. I would think that there would be a decrease in pressure if you're on Mars, but no, I don't know. I could be getting the physics wrong. I'm not 100% sure on that. So anyway, we went over the Hyperbaria and the increases in pressure as we go below the surface of the water, the physics behind it, the reason why the pressure increases and increases so much, and some of the problems that can occur, such as the bends, and also having the increase in pressure physically on the body. One thing I didn't necessarily go over is that as somebody is deep sea diving, and I think that they go over it in some videos you might see online. In fact, that again, one of the videos that online below the 60-minute video, go ahead and watch that. One thing that I didn't go over was that if you're ascending to the surface, and if you had just breathed in some air, inhaled and filled up the lungs at an increased pressure, and then you rise to the surface, you need to let out some of that air to decrease the volume, or the lungs will expand, and they could expand to the point where they rupture, not just rupture, but literally almost explode. There have been cases of this. So alleviating some of that volume, so decreasing some of the volume, breathing out some of the air, is certainly going to help to hopefully not allow that to happen. And that would not be a good thing. Not going to have a good time. Okay. So anyway, those were some of the concepts behind the Hyperbaria. I hope you enjoyed the chapter. If you have any questions, you have any comments, anything like that, let me know. Email me. Call me on the phone. I don't have TikTok or anything. So, I don't know. Is TikTok a messaging server? No, I don't think it's, I don't even know where I'm going with this. Getting squirrely again. I don't know. So I'll just sum this up by just saying thank you for watching. Hope you enjoyed the chapter. We'll continue on with a couple more chapters. Next up is going to be hypoxia. So going above sea level, well above sea level. And I'll see you then. See, little man, you French fried when you should have pizzaed, okay? Not gonna have a good time, okay?
That's terrible. That's terrible, terrible, terrible.